we will now talk about Hahn-Banach theorems. There are several theorems which go under this name. They are basically the same thing, and there are essentially two kinds of Hahn-Banach theorems. First is called the analytic version, which deals with the extension of continuous linear functionals defined on a subspace to the whole space. The second one, known as the geometric version, deals with how you can separate convex sets in the vector space by means of hyperplanes. Okay, so these are the kinds. So we will first look at the analytic version. So theorem. So Hahn-Banach. We are going to first prove a fairly general result, and then we will deduce the extension theorem as a consequence. So let V be a vector space over R. So now I am specifically saying that this is a vector space over R, and let P V to R be such that P of x plus y is less than or equal to Px plus Py, and P of alpha x is alpha times P of x, and this is for all x, y in V, and this is for all alpha greater than 0 and x in V. So this looks like a norm, but it is not precisely a norm. Okay. Let W be a subspace of V, and let G from W to R be linear. So it is a linear functional, not necessarily continuous, because we do not have a norm or a topology as yet. This is just a vector space with a function mapping P. So let it be linear such that Gx is less than or equal to Px for all x in W. Then there exists a linear extension f from V to R such that fx is less than or equal to Px for all x in V. So what do we mean by linear extension? This means f is linear and f restricted to W is the same as G. So this is what we mean by a linear extension. Okay, so we are going to prove this using Zorn's lemma. So proof. So let P be the set of all pairs YH. So Y is a subspace of V and Y contains W, and H is a linear extension of G. Because Y contains W, we can talk of linear extension of G, and Hx is less than or equal to Px for all x in Y. So this we are going to talk. So P is non-empty because you already have W comma G belongs to P. So now we are going to define a partial order. So if you have Y1 H1, we say it is less than or equal to Y2 H2 if Y1 is contained in Y2 and H2 is a linear extension of H1. So this defines a partial order on the space. Okay. So we now take Q to be a chain. I belonging to some indexing set I, a chain. What is a chain? A chain means any two elements are comparable. If y1 h1 and y2 h2 are in Q, then either y1 is contained in y2 or y2 is contained in y1, and corresponding maps are linear extensions. So any two maps are comparable. So then you define y equals union yi. This again a subspace because this is a chain. Given any two elements, they belonging to some yi and yj, but then one of them is bigger than the other, so both will belong to say yi or both to yj. So x plus y will again be here. So also with the scalar multiplication. So this is a subspace, and you define h on y to r such that h of x equals hi of x if x belongs to yi. Again, this is well defined because if x belongs to yi and yj, then it will belong to the bigger one because they are comparable, and therefore hi of x will be the same as hj of x. So it does not matter, this is well defined if you because of the fact that you are dealing with a chain. That is the important thing. And then clearly h is a linear extension, so h is obviously a linear extension of G. Therefore yh belongs to P. So every chain has an upper bound, and yi hi is clearly less than or equal to yh for all I. Therefore every chain has an upper bound, and therefore by Zorn's lemma there exists a maximal element ZF in P. So what is a maximal element? There is no other element which is bigger than this according to this order relation. Z contains W and F is a linear extension of G. So these are all the properties. So we will be through. So to complete the proof, we need to show, or it's enough for us to show, that ZF actually belongs to P. ZF is in P, that we know already, sorry. Z equals V. So if we can show this, then of course we have proved that there is a linear extension to the whole of V. So assume the contrary. So assume not. So there exists x0 belonging to V which is not in Z. So now you define y equals x plus t times x naught, where x belongs to Z and t belongs to R. So this is y is a subspace which of course contains W, because we put t equal to 0, it will contain W, and of course it strictly contains Z. So y strictly contains Z. And now I am going to define a mapping H of x plus t naught, tx naught, sorry, as equal to f of x plus alpha times t. So alpha to be determined. How do I want to determine alpha? Alpha to be determined such that yh also belongs to P. Then we will have a contradiction because we have contradicted the maximality of ZF. So we want to see if we can do this. If we can do this, we have a contradiction, and therefore Z will become equal to V, and you have the maximal extension will be what we want to do. Okay, so y already contains W, so H is also linear, so we only want to show that Hx is less than Px. So what do we want to do? We want to choose alpha such that fx plus alpha t is less than or equal to P of x plus T naught, Tx naught. This is what we want to show. Okay. Now, if T is positive, divide throughout by T. So, you have f of x by T plus alpha is less than or equal to P of x by T plus x naught. This is true for all x and for all T positive, and that just means, so this implies that for all x in Z, you have f of x plus alpha is less than or equal to P of x plus x naught. Now, if T is less than 0, you divide by minus T, okay, and then do the same kind of calculation. So, you will get f of x minus alpha. So, just verify this, less than or equal to P of x minus x naught, and this should be true for all x in Z. So, what we want to do is, so to find alpha such that sup of x in Z, f of x minus P of x minus x naught less than or equal to alpha less than or equal to inf of x in Z, T of x plus x naught minus f of x. If we can do this, then both the previous inequalities will be satisfied, and therefore we would have achieved our purpose. So, up to now we have used only one property of T, namely positive scalars can go in and out of P. So, we now want to use the other property, which is like the triangle inequality kind of thing. So, we take any xy in Z, then you have f of x plus f of y. This will be f of x plus y, and that we know because f is already in the script P set, therefore this is less than P of x plus y, and that is less than or equal to, I add and subtract, so P of x plus x naught plus P of y minus x naught. So, we have f of y minus P of y minus x naught is less than or equal to P of x plus x naught minus f of x for all x y in Z, and therefore the sup of this quantity is always less than the inf of all these quantities. Sup of the left hand side is less than or equal to inf of the right hand side, and therefore we can always find an alpha such that this is true, and this completes the proof. Okay. So, now we have the theorem. I will again call it Hahn-Banach. V norm linear space over R, W subspace, and G from W to R continuous linear functional. Then there exists f from V to R continuous linear functional such that f restricted to W is G, that is, it is an extension, and as a bonus we also have that norm f in the dual space is nothing but norm G W star. So, we can preserve the norm of the linear function. So, not only can we extend it, we can also do it without the norm going out of control. Okay, proof. So, we are going to define P of x equals norm G in W star times norm x. Then obviously from the properties of the norm, P of x plus y is less than Px plus Py. P of alpha x for alpha positive is alpha times P of x. So, P satisfies both the conditions which we have. And we also have that Gx is less than or equal to Px. So that is also true, because in fact mod Gx is less than or equal to norm G times norm x, and therefore we have this. Therefore there exists f linear, f from V to R by the previous theorem, such that f restricted to W equal to G, f restrict W equal to G, that is right, and of course fx less than or equal to norm G W star times norm x. So this implies that f is continuous, and you have that is f belongs to V star, and fx less than or equal to norm G times norm x. So it is all true for all x, so you put x equals minus x, so it is true for minus fx also, so it is true for mod fx, and therefore you have that norm f is less than or equal to in V star is less than or equal to norm G in W star. Conversely, but f is equal to W in G, therefore we have that, so f equals G on W, and this implies that norm G W star is less than or equal to norm f V star. Because you are going to a bigger space, you are going to take the supremum of mod fx over a bigger set, and consequently you will have a bigger supremum, and this implies that norm G W star is the same as norm f in V star. So this proves the Hahn-Banach theorem completely. Okay. So now let us, so this is one place, because we are dealing with inequalities, of course we only have to deal with the real vector space. So now we want to prove the extension theorem also for a complex vector space. So before we do that, we want to look at the anatomy of a continuous linear functional on a complex vector space. So proposition. So V is a norm-linear space over C. Now F from V to C continuous linear functional. So then you write F equals G plus IH, the real and imaginary parts of Fx. Okay, Fx equals Gx plus I times Hx. So these are the real and imaginary parts. Okay, then Fx equals Gx minus I times G Ix for all x in V, and norm f in V star is same as norm G in V star. I will put real here. What does it mean? Okay, now V is a complex vector space. If you just restrict to scalar multiplication by reals, it is also a real vector space. And if you write f as G plus IH, the real and imaginary parts, then G and H are linear functionals, or in fact they are continuous linear functions, we will also see that, on the real vector space V. Okay, so and we claim that the norm f, so the real part alone decides the entire functional, and in fact the norm is also the same. So the real part is the major thing, and that is why we can extend the previous theorem. Okay, so let us do that. So we take, so proof x in V. So now f of Ix equals I times f of x. So we get G of Ix plus I times H of Ix equal to I times f of x, which is Igx minus Hx. Therefore you have Hx equals minus G times Ix, and therefore we are through. Okay. So this proves the first part, namely fx can be written entirely in terms of the real part because of the linearity, the complex linearity, which means I plays a part in the whole calculation. Okay, so now let us take mod fx. Every complex number can be written as e power I theta times its modulus. So we can write this as some e power minus I theta times f of x. F of x is a complex number, so it can be written as e power I theta times mod fx. So I am writing mod fx is this. But now e power minus I theta is a complex number, so and f is a complex linear functional. So this is e power minus I theta x, and therefore that is less than or equal to, that's equal to g of e power minus I theta x plus I times h of e power minus I theta x. But if you look at the left hand side, you have mod fx, which is real, so this part cannot exist, so automatically that has to be 0, and therefore you have this is less than or equal to norm g times modulus norm of e power minus I theta. E power minus I theta is mod 1 times norm x, and therefore you have that norm f is less than or equal to norm g. Okay. Now on the other hand, mod fx square equals mod gx square plus mod hx square. Therefore mod gx is less than or equal to mod fx, which is less than or equal to norm f times norm x, and therefore norm g is less than or equal to norm f. I am not writing the subscripts of the place, it is clear from the context what I am talking about. Therefore you have that norm g equals norm f, and the theorem is proved. So now we go on to the theorem Hahn-Banach. Again, V norm linear space over C, W subspace of V, and G from W to C continuous linear function. Then there exists f from V to C continuous linear, and norm f equal to norm g. So proof. So we will write g of x as some h of x minus I times h of ix, where h is the real part of g. Then you know that norm of g is the same as norm of h, where h is considered as a real linear functional over the real vector space V considered only with the field R. Okay, so then by the real Hahn-Banach theorem, which we have just proved, there exists h tilde from V to R such that h tilde restricted to W equals h, and norm of h tilde equals norm of h. These are all considering V as a real vector space. Okay, and now I am going to define f of x as h tilde x minus I h tilde I of x. Then if you can prove that this is linear, we are through, because the norm problem is not there, because norm f will be norm h tilde, which will be norm h, which we know is nothing but norm of g, and therefore the norm question is true. Now it is certainly vector addition goes through, f of x plus y is fx plus fy is clear. For any scalar, f of alpha x is alpha fx is also clear, because h tilde are all real linear functionals. So we only have to deal with the complex case, and by linearity it is enough to check for I. So f of ix equals h tilde ix minus I h tilde minus x, sorry, I of ix, which is minus x. So this minus and minus will become plus, so it will become plus I h tilde x. So I can pull out the I, so this becomes h tilde x minus I times h tilde I of x, and this is I times f of x, and therefore f is complex linear as well, and the theorem is proved. So in all cases, whether it is complex or linear, real vector space or complex vector space, if you have a norm-linear space and a continuous linear functional on a subspace, the Hahn-Banach theorem says we can always extend it continuously to the whole space, and you can preserve the norm. Okay, so now important corollary. So V is a norm linear space and x naught in V, x naught not equal to 0. Then there exists f in V star such that norm f equal to 1 and f of x naught equal to norm x naught, and which is obviously not equal to 0. Okay. So this says that the dual space is very rich. There are lots of continuous functional. For every x naught in V which is non-zero, I can produce a special continuous linear functional which is of norm 1 and whose value is a certain specific number. So we can specify whatever we want here, and therefore this really you can construct lots of linear functionals using this particular thing. So proof: you take W, which is a one-dimensional space, which is equal to G of one-dimensional space spanned by x naught. And then you define G of alpha x naught equals alpha times norm x naught. So in particular, G of x naught equal to norm x naught. Okay. Then you can extend f. So there exists f in V star, f restricted to W equal to G, and therefore this implies that f of x naught equals G of x naught equals norm of x naught, and norm f equal to norm G. But then what is norm G? Norm G is in fact equal to 1, because mod of G of alpha x naught is equal to mod alpha times norm of x naught equals norm of alpha x naught. So on the one dimensional space, G of any z is equal to norm z, and that means norm G is equal to 1. So norm f is equal to 1, and that proves this. So in particular, remark: if x, y are in V and x is not equal to y, there exists f in V star, norm f equal to 1 such that fx is not equal to fy. All you have to do is look at x minus y, which is not 0, and therefore you can find an f with norm f equal to 1, f of x minus y is norm of x minus y, which is not 0, and therefore fx is not equal to fy. So we say that V star separates points of V. That means given two distinct points, you can find a continuous linear functional which takes different values at these 2 points. So that property is called separation of points. So the whole family V star of all linear functionals is separated. Next is again a very interesting corollary. V norm linear space, x in V, then norm x equal to sup f in V star, norm f less than or equal to 1, mod fx, and in fact the supremum is attained, so I can write this as max f in V star, norm f less than or equal to 1, mod fx. Okay, so proof. So if norm f is less than or equal to 1, what about mod fx? This is less than or equal to norm x, and therefore the sup mod fx over f in V star, norm f less than or equal to 1 is of course less than or equal to norm x. On the other hand, we already found there exists f in V star and norm f equal to 1 and f of x equals norm x by the previous corollary, and therefore you have that the supremum is in fact equal to norm x, and since it is attained for a particular functional, in fact it is equal to the maximum. Now this is the starting point of a very interesting concept which we will see next.